A person who is not properly trained and he uses the microscope and give you the result, your first question should be, was the microscope at the correct eccentric height? That correction was made. If no, then you can't rely on that result. The second thing I told you yesterday, that is, has the microscope been calibrated? If there is no calibration, then you are wasting your time. Calibrations are done in two things, through two ways. For image calibration, you have cubic gold crystal, and the cubic gold crystals has atomic planes like this. These are the atomic planes of gold. And for example, the a-axis is 5 angstrom, right? And the b-axis is 6 angstrom, let us say. And you took image of the same crystal lattice and you measure there that how much are the distances between along the A-axis and B-axis. And here they will be in centimeter because you can't measure in angstrom and on the image. So when you measure there, the 2 centimeter distance represent 5 angstrom. This was known to you that the gold crystal has these interplanar spacings, and you took the image. So the real and the image are compared. When you measure the interplanar distance there, and it comes, for example, 5 centimeter between two atomic planes, and that particular along that axis, then you say that 1 centimeter corresponds to 1 angstrom. So 1 centimeter on the image corresponds to 1 or 1.5, whatever your calculation is, corresponds to 1 angstrom. Then when you put an unknown sample there, then you know that 1 centimeter on the image corresponds to 1.5 angstrom. And that is the image calibration. Again, when you are taking image, the eccentric height must be corrected. All the focusing of the microscope must be at optimum level. The voltage must be the same. The accelerating voltage of the machine must be the same for which you calibrated the machine. For 100 keV, it will be 5 angstrom will correspond to 5 centimeter there, or 5 centimeter image will correspond to 5 angstrom here. But if you change the voltage, when you change the voltage, accelerating voltage, E is equal to h nu, and nu is equal to c by lambda, right? So when you change this, you change lambda. So when the wavelength of the electron change, then the image and the diffraction pattern are both affected. They are related with this lambda. So when you calibrate the machine at 100 keV, then your calibration is valid for that voltage. If you do it for 200 keV, then your calibration is valid for that voltage. And in the diffraction pattern, you are considering the camera length as well. That how much is the camera length, and the microscope we usually use, it is, for example, 100 centimeter, it is 120 centimeter, it is 80 centimeter, and when you change that, then you are changing the reciprocal lattice spacing. You are enhancing the magnification. When you increase the camera length, you are looking from here and the beams are coming here. So here the light, the electron beams will be falling on a limited area. But when you increase the camera length, then the light will be falling on a larger area, right? So the interplanar distances on the reciprocal and the diffraction pattern, the distances between the points on the diffraction pattern, the spots, will be longer in comparison to the one which was here. So the camera length, the voltage, and the focusing of the machine must be same and perfect before relying or further going in the electron microscope research, right? So you did image calibration with known planes of gold. People usually use a thin film of gold for that. And for the electron diffraction calibration, I yesterday also told you that compare the geometry you see in the image and in the diffraction pattern. If this is the 001 zone axis taken from the same image, then this is 100 and this is 010. 010 means B axis and 100 means A axis. The angle between the two, is it 90 or not? Or what it is, you should measure it. And not only one angle, measure the angle, this one, then this one, and this one. This one and this one, then this one and this one. So measure multiple angles and then check theoretically, is the angle between 100 and 010 90 or something different? Is the angle between 110 and 100 is 70 or 60 or 50? So when you do calculation of the interplanar angle and the interplanar spacings from the R spacing, and they are both matching the angles as well as the interplanar spacing, then you say that my diffraction pattern is this zone axis of the material. Otherwise, you will try other options. Is it 001 zone axis? It is 011 axis, because there are many possibilities when you are looking into the diffraction pattern, right? So the geometry, the interplanar spacing in the reciprocal space, when they are larger distances, then they should be smaller in the image. And larger in the image will appear shorter in the reciprocal, the diffraction pattern. So you are here matching the reciprocal space with the direct space. And direct space is the reciprocal of the reciprocal space. So the larger will appear smaller and the smaller will appear larger. And the whole skill of microscopy, diffraction, is that you make invisible thing, unresolvable thing, resolvable. You have angstrom size, a few angstrom levels unit cell, and you are making it visibly with the naked eye, because you are reciprocating the dimensions of the unit cell. You can't enter the unit cell, but you reciprocate it in such a way that it appears like a three-dimensional room, a cubic room, instead of the few angstrom size small unit cell. And that is the what you say, the miracle of the diffraction pattern it does, right? The other thing which I told you, When you took that diffraction pattern, and I told you that you will need a camera constant, if you remember. In the old days, the microscope diffraction patterns had no calibration on the image, on the diffraction pattern or image, right? There was nothing on it that what are the dimensions here? Are these two 10 centimeters away? And the centimeter corresponds to angstrom, nanometer or meter. There was used to be nothing there, and you had to calculate the camera length. And the camera length calculation, as I told you, we will come back to this. Yeah, we used to measure the interplanar spacings, interspot distances along this direction, that direction, wherever we saw spots, right? When you measure those distances, they call them R1, R2, R3, R4, R5, and go on. For all spots, you can measure the R spacings. They will appear like this. As an introduction, for example, I have this, 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 and I selected, for example, this is the origin. This is one angle. This is the second angle. This is the third angle. And this is another angle. So this corresponds, for example, to 100. This corresponds to 110. Say, this is, for example, 210. This is 010. This is 020. And in this way, you move. So all these spots corresponds to specific planes. And planes in a unit cell, as you remember from your last course, that planes are like this, like this, like this, like this. So this is one plane. So what should be the angle between this plane and this plane? What should be the angle between this plane and this plane? So there are fixed interplanar angles. So only the value of D is not enough to say that this is this plane. Is it at that particular angle or not? So when both angles and the interplanar spacings are matching, then you decide that yes, this is this particular plane, right? So when you measure all these angles, and this is R1, this is R2, this is R3, this is R4, this is R5, and go on. You measure these, and then if this crystal is known for calibration, people usually use single crystal silicon, right? In X-ray, people usually use single crystal silicon or quartz, right? So when the D is known and the R was accurately measured, the D is known and the reciprocal lattice vectors R were correctly, accurately measured, then you got a shift R1 D1 is equal to X, say, R2 D2 is equal to x1, x2, r3, r4 is equal to x3, and so on. Right? All these give you the RD values. R measured from the diffraction pattern and D already known for the sample. You put the known sample and you verified that particular D spacing from the X-ray diffraction as well, so that there is no error or mistake. Once you have done that and you found RD is equal to 30, say, then this is your camera constant. And when you get this camera constant, then measure R for the unknown diffraction pattern. Right? When you have known this, then measure R for the unknown diffraction pattern, and 30 is equal to R is known and D is unknown. So your D will become 30 for R1. D1 will be equal to 30 over R1. And this 30 is called lambda L, which is equal to RD. And this is from diffraction conditions. It will come in our way why people say lambda L is equal to RD. Right? And this lambda L is called camera constant. Camera constant is fixed for a fixed accelerating voltage and fixed camera length. You can change the camera length by clicking a knob, by moving a knob. You can change it from 80 to 100 to 120, and that change in camera length increases the interspot distances. So when the spots are very congested together, so that you cannot resolve them easily from one another, then you increase the camera length so that they become resolvable. If the spots are too far from one another, then you decrease the camera length to bring them to a reasonable space, which are presentable, which are easily calculatable. This was the case when we had no specific calibration or mark from the inside of the machine.